Hello. Today I'm going to talk to you a little bit about how to model the Antoine equation. So I have previous videos, the first one being what the Antoine equation is, kind of giving you the background of what we're doing here. And then my previous video was how to get website data. So first we're going to take all of the content from this sheet and put it into this model Antoine equation. If you haven't seen my last video, I go through exactly what all of this stuff is and what it means, and a little bit for how to play with the inspect element. So now that we have all of this information, this is simply just grabbing data and creating a string for it, or a set of strings for it. Unfortunately, as we've imported it, it is not quite usable as data. It is currently a string, which, for those who aren't familiar with coding, a string is simply like a word. However, these words take the form of numbers, and it'd help if I could spell. As we get into this, we'll kind of get to understand a little bit more of how to convert these numerical strings into data, so we can create a model for them and determine what our A, B, and C of the Antoine equation is, or these constants that were experimentally determined. So we've essentially pulled the experimental data of these the pressure temperature relationships, and now we're going to create, in a sense, the Antoine equation. Fortunately, the relationship was set for us way long ago, so we don't have to guess on how to make numbers equal each other. Very important you recognize your ability to type and spell, because I am not good at it. So bear with me. So a little bit more about what I'm importing. So a lot of these websites or a lot of these repositories have some amazing computing capabilities, and we're going to kind of delve into the utilization of, but don't be afraid to look outside this video for a little bit more about the amazing things that JAX NumPy and JAX can do. As most things do in this world, as the NumPy is made obsolete, is replaced by something way better. In this case, it is JAX, and JAX is this pretty amazing computing tool that Google recently tried to get a lot more information, tried to get a lot of really neat computing software done as it. So I made a mistake somewhere. Let's find out what it is. So we're going to, from the plotly subplots, we're going to import the library of make subplots. We're going to, oh, I made this mistake before. It's okay, everybody makes mistakes. Everybody has those days. Everybody remembers Hannah Montana. And that should work. Whoa, what did we do? Plotly dark, valid error. Built-ins.string template layout plotly dark is not the way to do that. That's because the separator isn't period, it is underscore to mark space, not as a deeper delve into the library. My bad. We all make mistakes. It's important to remember that a lot of that stuff is reasonable. So I'm going to move my computer a little bit. Apologize if that made really loud or annoying sound. Now we're going to kind of get into how to convert this data from strings into actual usable data. So let's define the variable data. We're going to create it as a numerical Python array, and we're going to then we're going to create the variables for it. So we need pressure and or temperature and vapor pressure, which we're going to label as T and PVAP. Create a for loop. What's neat about Python, but is different in some other coding languages, you do actually have, or you don't have to end for loops. For those of you who are used to coding in, say, MATLAB, there is a requirement to end for loops, which Python decides that they are not going to do that. They're going to be way cooler than that and give you the opportunity to use indents to decide where the string or where the for loop begins and ends. So as I go through this and make a couple spelling errors, what I'm doing now is I am creating essentially recreating the table, but as numbers instead of numerical strings. And so for most of these types, we're going to create, so we need as a floating array, or a floating decimal, but we have a certainty that we're trying to give it to. Certainty is double. We're trying to make it doubly certain that we're getting the exact right things as we're searching for them. Be better if I kind of gave some more information to Python. So we're going to tell it that temperature is in the location in data at the 0 column, or the first column, because Python and a few other coding languages begin their counting for the array at 0 instead of 1, which I don't know how many times I have made that mistake of putting in the first array as 1 instead of 0, or vice versa, where I started an array at 0 and the language wants it as 1. So for those of you who don't recognize, right now we're inputting some information. So this is the this is the Antoine equation in our way. So this is our way of saying the log base 10 of the vapor pressure, of saturation pressure, equals our NP, so numerical Python, dot log 10. So this is a log base 10 of 1,000 times, and then this is our first or second column, so our vapor pressure. This 1,000 exists because the Antoine equation has very specific units, and we're in kilopascals, we need to be in pascals. So to normalize units, we've created this 1,000 times, and then everywhere there's a vapor pressure. Continuing on, there's an index error. Okay, too many indices in this string. So let me look. This NP array for T pressure vap in zip. And we're going to zip that together. So we've taken apart all of so when you create the NP array, you create a whole new array, and each one is their own thing. And for the zip, we zip them back up, put them back together in their table. And I have created too many files in the zip. There's too many zips in the zipper. Or, oh, it's in line 2. Line 2 is where I've created the problem. Too many indices for array, where t equals data. So we have an empty array. Empty array means something else went wrong. So let's go through and redo all our lines. Still have the area, or still have the error. They have t strings. Told exactly where to go. And then we have this data. This is our NP array. NP array has two columns, temperature and vapor pressure for temperature and pvap. We're gonna zip together back t strings. Data colon comma 0. Where am I missing the point? Somewhere. Things are weird. Well, I'll pause this while I figure out what's going on. All right, I'm back. So I found out the issue. If you go into this line, what we currently have is on or t strings. This XPath. I made a spelling mistake in the previous video. It is ddb-form. I accidentally put it as from. So that would give us our previous errors. There are too many indices from the array because guess what? We didn't have an array. So as we move through, so we have this log base 10 of the vapor pressure. So we've given it we've told it the Antoine equation. So now we're going to have it, graph our equation so we make sure that we know what we're looking at. And here we're just kind of creating the graph. It's got one row and one column. And we're going to tell it exactly what we want. We want a scatter plot. We can tell it to make a lot of different plots with fig.add underscore, and then we fill in what kind of plot we want. So if we go all the way to fig, it doesn't make sense. Okay, so if it had its suggestions up and ready for us, it would tell us that there are about 1,000,001 plots that we can make. So now we need to define what our variables are. So our x variable, temperature, as our previous graphs and figures have shown for our phase diagram, we had temperature on the x and pressure on the y. So we need to name our variables after what we want it to do. So now we want it to show us markers, because if we just put it in or if we left mode alone and we didn't name it, or if we left mode alone and didn't give it any form of direction, it would just draw a straight line for us. And if you've had any experience in the engineering world, anyone that you show a modeled line, or if you give them a line when it's a data curve, they will accept it as 100% false, because you can't model data. You have to create a model that fits your data, not data that fits a model. So as we have created all of our figure, update, and there's a problem. So log dat. Oh, don't forget, guys, to always keep consistent variables. There we go. Now we have a graph that tells us all these really cool things about all of our data that we have given it. So now we can zoom in. The cool thing about Python is you can zoom. You don't have to do anything odd to do it. So reset axes to all the way back to the beginning. Unlike Excel, where if you tried to zoom, you end up deleting data from your figure, but not with Python, which I think is really cool. So after our plot, so now we're going to try to create a line that fits this plot. So to do this, we're going to define some variables, and we're going to create a model. This model is going to have variables A, B, C, and T, which for those of you who have seen my previous videos, A, B, C, and T are all of the variables in our saturation, or they're all of the variables or constants in our Antoine equation. So now that we have defined this, we're going to have it return a variation of our Antoine equation, which is A minus, and you're going to put B over quantity C plus T. Now that we return our model, so part of this is maybe we have a compound that we don't actually know A, B, and C for, or we have undefined variables. So to help us kind of figure out what our compound is, or kind of give us an idea of what we're going to look for, we're going to try to guess at our A, B, and C constants, despite our A, B, and C being very well and consistently defined. We're just going to try to throw in some guesses and create a model that returns our true values and gives us the Antoine equation, or the Antoine constants for water. And to help us with our further use of this, we're going to create a matrix known as X naught. So we're going to have our guesses in there. So here's all of our guesses. And we're going to run this part of code. Okay, now to kind of help us understand where our kind of values are and our and try to get our accurate A, B, C, we're going to create what is known as a sum square error. So sum square error is something that you'll see a lot in statistics, and we're going to use it today to determine and create a fine-tuned model of our data. And this is going to be assuming that we don't actually know what A, B, and C are, that our compound is unknown, despite the data that we've imported being water, with very known and published data. So as we go through, we're going to tell it that our model is going to be of our guesses. So our A guess, our B guess, and I'm going to put in our C guess. As again, shouldn't be 3. There's only 3 variables, not 4, and then T. So we're going to create a model for all of these. Then if we have an error, we're going to use Jack's NumPy, and we're going to sum it together in our model of vapor pressure minus our actual log 10 vapor pressure. And at the end of that, we're going to square it to create our sum squared error. And we want to figure out what our error is. And we want to kind of figure out what these results are. So to kind of help us figure out what these results are, we are going to use the minimize function, which, if you hadn't noticed, was the last thing that we imported, which is from SciPy, or Scientific Python. And from the optimize library, we're going to take minimize. So all of this code that has been put together for us by master coders, we're going to use to our end and create a minimize function for our sum square error. So our just kind of talking through what we're going through here. So we're using the minimize, we're inputting. This is kind of, so we're telling it what we want to minimize, what we're measuring it against. So x naught equals x naught. Then our arguments are t and log 10 pvap. Excuse me. And then we're going to tell Python that we want our tool to equal, or we want our error to end up only being 1 to the negative 10th or somewhat negligible. Then we're going to tell it a little bit more about our sum square error. And boom. Log base 10 pvap not, that is minor typing error. Oh, no GPU, TPU falling back to CPU. All right, so now that we've gotten this, we're going to see what our results are. Our results have given us the A, B, and C. And our A, B, and C, those A, B, and C are the actual values for A, B, and C of water. So if we look it up, go into Google, give us our best friend, Antoine constants for water. A, 8.4, and C. This is one of the several different versions of the Antoine parameters. So we have one of these sets of parameters. Woo! They all vary with temperature. So we have the Antoine equation, we have the Antoine constants for water. Yay! And they're actually correct. So now that we have these Antoine constants, we're going to model it against what our experimental values are to figure out how true they really are, to figure out how good they really are. So I'm going to drop it from numpy linspace. We want temperature at the 0 array. That'd be a problem if I ran through all that code and that silly mistake. So now that we have our t at a function of 0, we're also going to look at not the last one, but not the first entry, but the last entry. And 100 should end Okay, and then we are going to add a scatter plot. Woo! See, we can add a lot of stuff. Core math pops, contour, contour carpet, density funnel, histograms, whatever your heart desires or whatever the problem determines. But just to create a better model, we're just going to add a scatter plot. As that is the best and most base form of any plots. So we have our y, we have our x. Now to create the rest of our plot. So we want it to be, as we have the actual model, now we need to tell it that we want lines because we want to show it against the data and our curve of best fit. And to kind of help control some of the variables, we're going to create more information and define everything so we can actually see it all together. If we didn't create a line, we may get a line width that's way too great, so we won't be able to see our data points anymore because they will superimpose as it is the most recent model of data. And now that we have our two combined, we should get our model. So this shows that our Antoine equation that we experimentally determined or miraculously determined from creating the sum squared error and creating A, B, and C point guesses and then throwing it all together to try to create an equation, we have determined that our Antoine equation is correct. We've created the proper A, B, and C. We've created a model against it, and we've created a model to fit our data, which is an incredibly useful tool in a lot of engineering. That's really all I have today for modeling the Antoine equation. If you have any questions or wanted to refer back to anything that I talked about, I have 2 more videos. One will define a little bit more about the Antoine equation. The other is just how to grab data off a website. Everything else is right here. This is a combination of really everything that I've talked about. Besides that, thanks for watching.